to the lecture on computational heat and fluid flow. Yesterday we learned about the staggered grid. So we have the centered cell where we have stored the pressure and we have temperature, other scalar quantities, mass fractions and so on. And at the western face we have then with the same index but the lowercase I, we have the u velocity component. And to compute that, we have its own grid, which is shifted delta x half to the left. Here we have the example for, so here we have the example for ui plus 1, j minus 1. And the v component that is then at the southern face of the main control volume. And we have seen the discretization for the x momentum equation. And we want just to look at the coefficients. So the coefficients that we have there, then we have to decide which discretization we use for the convective terms. So the finite volume method for the x momentum equation, that was what we discussed yesterday. If we choose now the upwind finite volume method. So that is now our choice for the convective fluxes. That yields a linear system for the preliminary velocity which we denoted by u star. And that is what we saw yesterday. I just repeated. That was equation 8. We had just given it without derivation, but now we give the example. You saw previously the equation that we get that was not containing the values. It was only containing the UE, the V, the U north, the U west, and the U south. Now we do the discretization then. And then we get this form here. That is our preliminary velocity at ij. That would be the one that we are solving for in the figure. That would be at the western face of the center control point. So that would be for this one that we are solving. And that is then equal to the sum over the neighboring nodes, A and B, and the coefficients there, and the preliminary velocities at those nodes. And we'll look at that now in more detail. And then we have some contribution from the pressure, that is the pressure force that is acting then on the control volume in the x direction. And there we saw this is this nice way of the staggering that we get the pressures exactly where we need them. That is then at the east, and that is the pressure then at the west face. So they are located exactly at the right spot, times the area, and then we have also some source term that is coming from a volume force. So that is now the notation that the volume force that we were discussing, that we were mentioning yesterday, that is, let's see, that is the rho times the x component of the acceleration times the volume. So that is now our, so that here the B here, that is rho fx times the volume in the cell P, or here it would be then in the little ij. Okay, and this here now that we have here, that is now our uniform part of the source term. And the coefficients we shall see in a minute. The coefficients are the following, and that is now for the upwind scheme. And the derivation we can do just in the same way as we have been doing now for exercise 10 for the convection diffusion equation. However, there we do the central finite volume method. Here we have the upwind method. So that is the diffusion conductance at the western phase, that is lowercase w, plus the convective mass flux. We take the positive contribution. So that is the value, we take the value if it is positive, and otherwise we take 0. And the AE coefficient for the upwind method for the convective fluxes is the diffusion conductance at the east minus the convective mass flux at the eastern phase, and there we take the negative. That is, we take the value as it is when FE is negative, otherwise we take it 0. The AS is then just correspondingly, that is a uppercase S, diffusion conductance with a lowercase s at the phase, and that is then the corresponding the plus contribution from the convective mass flux at the southern phase. The northern, we have the diffusion conductance at the northern phase minus the convective mass flux to the minus. So, and the center coefficient, that is the AP coefficient, that is denoted here just by Aij, that is the sum of the neighboring coefficients, west, east, north, south, north, and we have, if we do this, we find out that we also have the convective mass fluxes coming in here. And this here, that is the sum of the neighboring coefficients. And this here, that is the discretized continuity equation. That is the net mass flux over the control volume. And if we have the continuity valid, so then the continuity equation, when that is valid, then this is 0. And of course, the thing that I did not write here, but I can add it here, that is minus SP, if we have a contribution from the source term. But in that case, we don't have that. In our case, we have just, if we just look at this here, we just have a uniform contribution from the source term that is appearing here. So we have not a contribution in that case from the source. So in our case, this would be, in our case, 0. So then we do that, we include the boundary conditions, and then we have this linear system that is just the same as the convection diffusion equation as we discussed now for exercise 10 for the energy equation. Just similar, we can solve then this interdiagonal system that we get by some method like the alternating line Gauss-Seidel method, as we do now for exercise 10. Then, if we use an iterative method like the alternating line Gauss-Seidel, then we usually use under-relaxation. So in the iterative solution, of the linear system, defined by from equation 8, usually under-relaxation is used. And that is to improve the convergence. And that means that we do the following. When we do some iteration, then we compute the new value at the new iteration by a computer assignment. So that is again, as I use this notation here, as a computer assignment. As you do when you do the programming in Fortran or MATLAB or whatever you like. Then we have the value at the old iteration, and instead of adding the complete change, we add only part of the change. We call that alpha u, this relaxation coefficient, and that is then adding part of the change that we have from the new iteration to the old iteration. And for this alpha u, you find different values in the literature, but the one that is recommended by Raithby and Schneider, that is also used in the skeleton, or you can use in the skeleton, let's say that, alpha u is equal to 0.8. Other authors, for example, in the textbook by Ferziger and Perich, they use 0.7. Patanka used 0.5. But I think people are now using something rather like this. And the boundary conditions are then treated as we do now treat the boundary conditions for the energy equation. So it comes down to be very similar to what we already know about the convection diffusion equation. I would like to give you a little exercise, and the exercise is to derive the linear system that you get with the central finite volume method. So here you have now the coefficients for the upwind finite volume method, but as an exercise I recommend you to derive the system that you get for the central finite volume method for the convective fluxes. Okay, so then we know how to do that. And in the end, we have then computed the preliminary velocity by this implicit method. By this method here, because we have everything coupled, so we don't need to talk about explicit, implicit, everything is coupled. And then we know the velocity in the u direction. Now we do a similar thing to get the velocity components in the y direction, so the v. You see also here the philosophy of the skeleton program that we have been now extending now to 2D, first only diffusion and now convection diffusion, and now you can apply it here to solve the x momentum equation. The same way we'll do it for the y momentum equation. So that is the finite volume method for the y momentum equation. And just to make sure that we do are sure about the grid that we are now using, we now make a little sketch of the staggered grid that we use for the computing the v, the velocity component in the y direction. So we have again these 3 by 3 cells to indicate now what we are doing here. So what we're doing, we want now to compute the velocity component in the y direction. And that has then the index capital I, lowercase j. And to know where we are in our picture here, remember that is the southern face of the general control volume. So that is here. So this here has the index v, capital I, lowercase j. So there we are now computing the velocity component in the y direction. So then we just get the neighbors, because they shall be needed. This is I plus 1 j. This is I minus 1 j. And this is I j plus 1. And here this is I j minus 1. J minus 1. So then we have the u velocity components and the y velocity components where v is situated. Now we need also to know where u is. So so if you look at that, so in relation to the, so you see this is the one that is at the southern. So then the velocity component, this one here, that would then be the uij. Let's see, yes. So here in this corner, we'll have the uij. I just write the indices. That is then lowercase I, capital case j. And here we have the neighbor. That is then I plus 1 j. And below we have, here we have then also I, but capital J minus 1. And here we have I j. Let's see if that is right what I'm doing. No, that is not right. This is I plus 1. So it's the same I plus 1 j. So now I think if that is right, let's see. No, it is j minus 1. So now I hope it's right. Let's see. Okay. So you see, this is I, and that is also the location where, so there here we have then the eastern face, here we have the western face, there we have the northern face, and there we have the southern face. There we have to compute now our momentum fluxes for the y momentum equation. The thing that is missing now is the pressure. And if we look up here, we see that the pressure Pij is just above. So that means the pressure that is located here, that has then the index capital I, capital J. And on the southern face, we have then also I, but J minus 1. Capital I, J minus 1. You see here the u velocity is at the same J minus 1. And here the u velocity here is at the same J. Okay, so then we have our indices, and now we can do the discretization. And remember, this grid is coming from the original grid by shifting it delta y half down to the south. So then we solve now the y momentum equation. To determine the preliminary velocity component Vij star. And the equation that we have to solve is then the following. we have the integral over control volume. In our case, it will be the control volume for the cell P. And here we have now the momentum flux for the y direction. So rho v times the normal velocity component, u dot n surface integral. And on the right hand side, we have the viscous force acting on the control volume, and for constant viscosity that can be expressed as viscosity coefficient times nabla v. The nabla gives the vector. We take the inner product with the outer unit normal vector n. We integrate over the area. And then we have now the pressure acting in the y direction. The pressure force in the y direction. So that is then giving us a contribution minus integral over the boundary of the control volume. And then we have P n y, y component of the unit normal vector n. Surface integral, and then we might also have a source term, which would be, say, rho f y dv. So that would be then our y momentum equation in integral form. And then we do the discretization in the similar way as we did for the x momentum equation. We compute all the fluxes, those the convective and the diffusive fluxes. We consider the pressure force and the volume force. So let's do that. And the first thing is we compute the convective mass fluxes over the different faces. So Fe, there we have to compute then rho u times the area, and u we have available here and here, so we can use that. So that is then 11A. That is then the convective mass flux at the eastern face, and then we do the average of the values I just pointed out of rho u. We take that directly, and that is then I plus 1 j minus 1 plus rho u at I plus 1 j. So that are the values here and here. We shall do it in the same way at the western face. We don't need to write that. And at the northern face, we will need the V, which we have here and here. But first we have to complete this by taking here the product with the area, which is in our case delta y. Then we take the northern, I just mentioned it already. There we need to take the rho v, and that is then at ij plus the rho v at ij plus 1. And that is then multiplied by the area at the northern face, which is delta x. In similar way, then we do that at the southern face. The diffusion conductances, they are determined then in the following way. That is the standard way. So we have the mu viscosity coefficient, and then the distance between, in that case, I plus 1 and I in x direction. And when we need to compute it for the northern face, we have to have the distance between y here and y here. So there is y at j plus 1 and y at j. First here x, that is xi plus 1 minus xi times the area, and the northern is then the viscosity coefficient. I just select the y, j plus 1 minus yj times the area at the northern face. So then we have here our coefficients that we need. And the values that we use here for U and V are the latest values that we have available in our iterative process. The pressure that is entering, that will also be taken at the latest value of the pressure that we have. So now we can then do the evaluation. So to determine the preliminary velocity, that is the V star, the component in the y direction. This equation 10, the y momentum equation, is discretized like we discretized the x momentum. And we get then the following. Let's see. So the equation that we get by discretizing this, I write directly the result with the coefficients. That will be, the coefficient will be then at ij, that will be the center coefficient, times the unknown, that is the V star at this node. On the right hand side we'll have the sum over the neighboring nodes, neighboring coefficients, and the velocity V star at these nodes. And then, so then we have taken that into account, again deciding on whether we use an upwind finite volume method for discretizing the convective fluxes or the central finite volume method. This is anyway discretized by the central finite volume method. And then we have here the contributions from the pressure. And now you see we have to compute here the pressure force in the y direction. And there we will only get a contribution from the northern and from the southern faces. And you see we have exactly now the pressures where we want them. They are exactly at the right place. Here at the northern face we have the pressure Ij, at the southern Ij minus 1. And we can just use them. So then we get the following. That is then the pressure, and again, I mentioned before, that is the latest available iteration value for the pressure. That is Pij, that is at the northern face, minus P star at Ij minus 1 at the southern face, times the area. The area, you can take it as Ij, the area that is the same. Let's see, I think I took here this smaller. It doesn't matter if we have a larger, it's the same anyway. And that is then the force, the pressure force. And then we have also a contribution that is coming from the volume force. In our case, that is then the rho, the y component of the acceleration times the volume, and that is then Ij. And this quantity here, that will later be denoted by B. B Ij. So, and then we have here our equation that we solve. And you see here again, including the minus here, this part will be then the uniform part of the source term. And the coefficients are then similar as we discussed for equation, discretization for equation 4, the x momentum equation. And the boundaries are treated again in a similar way. In the iterative solution, of this equation 13, usually under-relaxation is used again to accelerate convergence. Under-relaxation is used to accelerate convergence, and that is done in a similar way as we discussed before. I call it 13a here, that the preliminary velocity at the new iteration is assigned, again a computer assignment as before for u star, the value at the old iteration plus a relaxation coefficient alpha v times the difference between the value that we would get normally with at the new iteration minus the v star at the old iteration. And the alpha v, the relaxation coefficient for v, is usually chosen equal to alpha u. So where alpha v is chosen equal to alpha u. In our case, for the it will be 0.8 if we take the value used by Schneider. Okay, so then we then at the end, when we are finished with that, we have also the preliminary velocity components v star. So before we have determined the u star at its proper values, now the v star. And then we have to determine the pressure. That is now the task that we have to do. You see, for doing what we have discussed now, solving for the preliminary velocity component v star and previously for u star, we can simply use the method that we have been now developing for exercise 10 to solve a convection diffusion equation in 2D. It's just filling it with the correct coefficients, with the correct source terms, and then we just solve it, for example, by the alternating line Gauss-Seidel method or whatever method you like. So then we look now how to get the pressure. And for that we use a method called simple. That is also the name of the main program in the skeleton code that you got, that you're extending. So the simple algorithm. Again, an acronym, and that is coming from the following. So simple stands for semi-implicit method for pressure-linked equations. So that is the acronym, and that is due to Tatanka and Spalding. From Imperial College in London. And the idea of this is to correct the preliminary velocity components such that the continuity equation is satisfied. So let me write that. So the idea of simple is, and similar methods. There are a couple, I'll mention some later on, there are, and it is also true for those methods. So for simple and similar methods, is to correct the preliminary velocity, the preliminary pressure, that is the preliminary pressure, that is the to correct the preliminary pressure and the preliminary velocity components such that the continuity equation for incompressible flow, that was equation 3, is satisfied. So then we have a criterion to determine the pressure. That was lacking so far. So then we assume that the solution will look like that. It is called an ansatz. That we assume that the pressure that we should get in the end is equal to the preliminary pressure plus some pressure correction. So the P prime is the pressure correction. That is the one that we have guessed in the beginning, or it is the latest iteration value of the pressure. And this here, that is an answer, but we will change that later on. That will be modified later. So I'll come back to that. I just warned you in the beginning. For the velocity, we do something similar. We correct the preliminary velocity with a velocity correction, both for the x and for the y momentum equations for those for the x and y directions, and that is the v star plus the v prime, and these are not changed. So because we rely on this form of the representation of the velocity components. So the idea now is we assume we want to determine these p prime, u prime, and d prime. So the goal is that we solve the whole system correctly. And that is we imagine we can do that. So we suppose now that the pressure, the velocity components u and v, that they satisfy the continuity equation number 3 and the momentum equations. So we imagine that this is the solution to our problem. And that is then the momentum equation that would in our case correspond to, let's see, it was corresponding to 8 and 13. That is the momentum equations, let's see, yeah, right. That is okay. So discretized x momentum equation, so the discretized x momentum equation that is then corresponding to equation 8 for the preliminary velocity component u star, that reads then with, say, with the correct values, that would read then something like that, that we have, we assume we have the same coefficients, but now we have really the correct values for u, not the preliminary, but the correct values. The relation is the same as we had discussed before. The relation to the neighboring, with the neighboring values u and b, the neighboring coefficients a and b, and also the pressure force that is acting but now with the correct pressure, Pij minus Pi minus 1j times the area and the source current. That is describing the volume force in that case. So we assume that that is really solving the problem for the grid that we are considering correctly. And then we subtract equation 8 from this correct equation. 8 was the preliminary velocity equation. So subtracting equation 8 for the preliminary velocity components u star from this equation 16, we get the following. Remember, the original equation had just the same here, but just the u star. Here the u star, here the p star. The b was the same. So if we subtract that, and we use that u is u star plus u prime, v is, no, that we don't need yet, only this, and p is p star p prime, then we get in the end the same equation, but for the u prime here, p prime here, this is the same, that will cancel when we subtract the same value. So then we get the following. That is equation 17. We get the same coefficients, Aij, and now the velocity corrections, u prime, equal to the sum over the neighboring of the neighboring coefficients, times the velocity correction at the neighbors. So that's the u prime at the neighboring coefficients. And the pressure, the same. We have the pressure correction, the p prime at ij minus, there's a capital J here, p prime at I minus 1j. And that is times the area at ij. So that is then an equation for the velocity corrections getting a relation to the pressure corrections. So, and now what we want to have a relation between the u prime and the p prime. And this is a hinder, because then if we have these guys here, we have always the neighbors. So then we cannot get a direct coupling. So the idea of Spalding-Patanka was simply to neglect that. Then we get a direct coupling between the velocity correction u star, u prime, and the difference of the pressure corrections. So that is then, so in order to get a direct coupling between velocity and pressure corrections, is approximated and that is now special for simple by this approach by Patanka and Spalding, the simple approach as the following. That is then routine that we say the Aij, capital J, the u prime at ij is equal to, and now we neglect this. We only take this. Minus the pressure correction at ij minus the pressure correction at I minus 1j. times the area. So simple approximation means that in the relation between velocity and pressure corrections, we neglect the contributions from the neighboring nodes. And we shall do then a similar approach for the getting the corrections, the velocity corrections in the y direction. And then we shall use this. So then you see when we divide by Aij, we get an expression for Uij relating that to the pressure corrections P prime. And then we have here the U is the U star plus U prime. Then we replace the U prime by this divided by the center coefficient. Then we have the P prime difference here appearing. We have U star plus that. And then the condition is that the net mass flux, that is the continuity equation, is 0. So that gives us then a condition. And that will give us a condition then to determine the P prime. That is the idea. Okay, but we'll do that after the break.